number 3. And what I'm going to do is I'm going to essentially focus on contrasting the SN1 and SN2 reaction, what are the differences, and also E1 and E2 reactions. And for first, I am going to solve the problem right away. These are the problems that was introduced to you before. And the first subject is electrophilic addition. And this is asking that, okay, you have an HCl here and there's a double bond. And this step is essentially protonation. But they are using the proper arrows. Arrow is about the electron movement. And so your electron moves to form a bonding with a hydrogen. Hydrogen is already dissociated. HCl is already dissociated into the H plus and Cl minus. So they are going to form the bonding. So I am going to use the same color as the text. So this one you used to have a cyclohexane. Right? I'm just going to show you the two different scenarios. The one is a methyl here. The one is a methyl here. Right? And then you have a hydrogen here, and that's on hydrogen. So that's coming before, and I'm going to use a blue color for the one that from the HCl. Okay, the hydrogen from the HCl. And so one is the one hydrogen can form the CH bonding here. By doing so, they develop positive charge on the other side. The other option is they can develop H here. They can develop the positive charges on the other side. Okay, so now you are going to develop this essentially good perspective. We are talking about carbocation stability, right? C plus stability here. And carbocation stability, C plus, carbocation stability here. And then I'm going to count the number of carbons surrounding this carbocation. 1, 2, 3, right? So that's the tertiary carbocation. And this one is 1 carbon, 2 carbon, and that's it. So that will be a secondary carbocation. And which is more stable? Tertiary carbon is more stable. Always remember that, and that becomes very important. And the reason is because you probably already know by now is methyl group is an electron donating group. Okay, carbon has a little higher electron negativity, so pulling the electron from hydrogen, and with the CH3, the net dipole is essentially electron donating group. So CH3 is an electron donating group. So therefore, this is very much more stabilized. The more you have an attachment of carbon hydrogen species, they are going to essentially stabilize the carbocations over there. So that's why you are having this. You choose this simply tertiary carbocation, and that's all you need to say here over the choices of A over B. And then the second step is okay. So now. This is a nucleophile that I'm going to form looking for something that is positive. And here we go. They are going to form the bonding. So that's why you are forming the CCl bonding right there. Okay. So that's the one that forming this. And because essentially what is the question is which way the chlorine will form, and essentially, right? In the kind of question was, this is a methyl hydrogen, and then you essentially find out chlorine likes to bond it to here, not to the other side. Okay, so that's the one that is what this problem is about. Second problem is a carbocation arrangement, and this problem is actually quite important. So I want to even develop this idea. Okay, so this is a very same as the one before. This is a 1 and 2, same as a 1. So first step is protonation. Okay, so this double bond will trying to make a bonding with a hydrogen. Okay, so that's what they do. And then now I am going to just draw the carbon skeleton, which is there is a C bond. C, 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 C. Okay, so this is the same molecule as shown before above, and then where do they want to develop? This is where they want to develop, right? If you think about it, they have a choices, this versus that, right? This is a essentially primary versus secondary. And so, okay, so this is out of question that no, this is not stable. So that's the one that they will form the protonation. But now, if you look at that, there is a chance that chlorine will just make a bonding to this chlorine. Chlorine make a bonding to this carbon on here. But if you look at that, if there is any possibility for them to enhance the stabilities by increase the stabilities of the carbocation by carbocation rearrangement. Okay, C plus rearrangement. In a sense that this is known as by how do you do that? Hydride shift or methyl shift. So we are talking about whole entire hydrogen with a carbon. So this whole thing, which is essentially hydrogen with a minus. That's why we don't call it hydrogen shift. We call hydride shift because there's two bonds, two electrons over there. Right? Those two electrons and everything will be shifted to the other carbons to neutralize the carbocation. So if you look at here, well, I don't see it here. There's a hydrogen here. But this one, by moving this side to the other, you are not making essentially the goal is two secondary carbocation to the tertiary carbocation. That's a very, very stable one. And so you cannot really do that because if you move this one to the other side, and then you are generating going back to this, and so that's not really what we want. So this is not going to happen. But now the other option is actually what is called a methyl shift. Okay, methyl shift is if you have a CH3, this is kind of the light enough. The whole thing can be moved, can be shifted. So this thing, so essentially CH3 with this lone pair, that's a negative one. This one is actually we should not call it methyl, methide shift. So if you look at that, some people actually call that. That's more correct name, but for some reason, the organic chemistry area, they always call hydride shift, and they like to call methyl shift. Methide is something a little bit difficult to pronounce, I guess, so that's their choice. So anyway, so the goal here is to make tertiary carbon from the secondary carbon by here methyl shift. That's possible. So how do I do? This is a CH3. The whole thing will form the bonding with a carbon over there. So that's the direction. So now you see that this methyl shift, which is CH3 minus, this compound is moving, and because of that, I think that the sound is really big. Let me reduce that. Okay. And so by doing so, what you are going to see over here is this is a compound that looks like before, and I'm going to use a purple color that is the shifted methyl. So they are forming the bond here. You see this CH3. This is it doesn't matter which one of the three, but I'm just picking up the one that from the other side. They can move, and this is a methyl shift, a methyl shift. By doing so, if you look at that, there's a positive charges here. You got to develop the positive charges here. And where does it go? Right here. Okay, that's the one. And then if you look at this carbocation right at the center, this one now have a carbon, carbon, carbon. This is a tertiary carbocation, right? So you successfully change the enhance the carbocation stabilities, and that will be something that we'll prefer. So second one is essentially methyl shift to make secondary carbocation to tertiary carbocation. Okay, so that will be something that is what they want to do. And so by doing so, once they have finished this is a second step product. And then I can just draw the chlorine, right? Chlorine is the one with lone pairs. They are looking for to make a bonding with a carbon right there. So therefore, you have this. Those are the one, and then there is a chlorine making a bonding here, right? So this is a CH3 and CH3, CH3, CH3. And then now you are going to compare the answers, right? This one is same as this one over there, right? So I'm just showing you that this is how this has happened, right? So if you first think about it, this is where the double bonds are originally located, right? So if you look at that, that's where the first time the double bonds are being located. So you might think that, okay, the protonation happens, one of the carbons here, and then the carbocation will be developed, and the chlorine will be attached to those carbocation site. But wait a minute, sometimes what you have is a secondary carbocation, right? The secondary carbocation, if you can make it into the tertiary carbocation by shifting the hydrogen or methyl, and then they will do. So therefore, that's why this is a position where the chlorine carbocation is newly developed, and by methyl shift, and then the chlorine is attached to that position. Okay, when they are competing for this the carbocation arrangement by hydride shift or the methyl shift, and if they are competing for hydride is the one that they will win the competition because that's the one that is lighter, so it's much more easier to move things around. Okay. I want to also give you an idea as a summaries. Now, if you see the secondary carbocation developed, certainly by hydride shift, methyl shift, you can do that, right? And also the other idea is if you have let's say carbocation in the secondary position, have you heard about the benzyl carbocation? This is also very, very stable carbocation. Have you heard about this? Benzyl carbocation? So let me draw the benzyl. Benzene is this, right? Benzyl is the extra carbons on there, and this is where the this is a carbocation. So CH, I guess a C, 1, 2, 3, CH2. Okay, so this is the benzylic carbocation position. So if I, for example, I can make up some questions just like, okay, so if you have something looks like that, and they CH and CH2, CH3. If they were to, some compound looks like a benzene group with CH, CH, CH3 carbocation. If this is the case, CH2, and that's the hydride shift will happen, and then you will develop this much stable carbocation because this is a resonance stabilization, and I hope that you guys heard about this. It's just a tertiary carbon benzyl carbocation is a lot more stable compared, but they are willing to go to the trouble of moving the hydride and the methyls, just like it's shown up here. Okay. All right. So let me go to the. We have a couple of people more join in, and thanks for joining in here this late night session. Today I'm going to more give you a contrast on the difference between the SN1 and SN2, E1 and E2 position. And here I found this example from the Dr. Ma's slide, and this one you can see this. Okay, I'm showing you this example where you can see that the reaction must happen by SN2. So SN2 means bimolecular, and SN means that this is one that you need to find out the nucleophile, which is an OH minus is electron rich. So that must be our nucleophile, right? We call nucleophile just like that. And that's the one that looking for the way that to attack the one. And if you're looking at this molecule shown up in cyclohexane, I love to draw this molecule in a way. Okay, so in a way, let me draw something looks like this. This is not actually flat hexagon. It is more buckled, and then if you're looking at that, there is a more like a chair form is what is known like. But if you're looking at the sort of the average plane, something going through this. So I'm just going to make sure that you guys can visualize this is on a plane. So I'm just kind of color this. So they are on kind of piece of this paper. Okay, this on piece of paper. This one is sitting on right here. Okay, and then what you can see here is now what this figure is saying that from this figure, when you see the chlorine just looks like this, that means the chlorine is moving away from the plane. So that's what this one. And then this the one that is sticking out, that means that this is a CH3. So you have things are sticking out of the plane or CH3. And because we said that this is an SN2, we want to see where your nucleophile. Okay, so I think that my pen is a little too thick, so now you can see that the nucleophile, which has this lone pair electron, in this case is OH minus. That's the one. Negatively charged OH minus. This has a nucleophile. It's trying to find the bonding, and where do they go? They are the electron rich. The other one is have a rich electrons, so therefore they are looking for something that is electropositive, and this carbon right here is a electropositive, right? So and then I just draw this orange plane. And that's where your hexagon cyclohexane ring is sort of on the lying flat, and your chlorine is pointing down, right? And then your thing is going to be moving from the top, just like that. So that what you can draw is a nucleophile will attack from the top. And if you actually looking at the Dr. Ma's notation saying from the top only, that's what he says. And if you want to draw it here, you can just draw like from the top, and that's what they mean by this. And so by doing so, what's the product that you are going to generate from this reaction will be the one that from the top. So therefore, now you are going to show your final product, which is okay. I'm going to draw this. And then with the leaving group is, this is a leaving group, right? The leaving group is a chlorine minus, right? So chlorine minus is your leaving group. So when they form the one, this one will leave just like that. So people draw the now structure looks like this. So I know that this before it was a methyl that was pointing up, and now you have a OH, which is also pointing out of the plane as an OH as a consequences of SN2. SN2, sorry, SN2. Okay, SN2 means substitution, right? Substitution, nucleophilic. 2 means bimolecular, right? Bimolecule. You need 2 molecules together. So think about this way. You need 2 molecule means this chlorine over here. It is kind of it's okay. Actually, it's not really bad, but it's compared to the other one, it will be a poor leaving group. Okay. More important, so it doesn't have its own motivation to leave as it is, but what you have over here is you have this OH minus, which is a pretty strong nucleophile. So it's more like it's a push and pull at the same time. Okay, this one is not like this is a chlorine. This chlorine is not likely to leave, so you need some kind of push and then pull at the same time. So that's a bimolecular. When you OH minus kind of poking onto the molecule, the chlorine has to leave at the same time. So it is a 2 molecule involves together, push and pull, and so therefore it's an SN2 reaction. So let me kind of draw some of the example that could be a different example. So I'm going to draw something very similar with a methyl here sticking out, but this time it's a chlorine. But this time I'm not drawing the chlorine, but instead I'm going to say H2O plus. Okay, so this is the one that I just drew here, and I think this is not okay. And then I can do this, right? And then the Cn minus, for example, right? So sodium Cn minus. So sodium plus Cn minus, and this is essentially C triple bond N, the lone pair electrons here, and then this is a very weak. Actually, this is a very weak, very strong nucleophile. So actually, I'm just kind of making up the nucleophile as I go along. So what I can do now is, why don't I do the sodium chloride? Why don't I do that? Okay. So this time you are making a chloride. Ion is your nucleophile. But this time this is a weak nucleophile, right? So this one doesn't really. They're supposed to look for something that is positive and it has to react onto here, but they are weak, so they are not gonna push this. They are not gonna push this. Actually, they are just going to quote unquote wait, okay, until the one before is dissociating by itself. Because when you look at the way that I choose this molecule now, this group is a very good leaving group. Okay, so they love to have these 2 bonds, two electrons in the bond, just taken by the leaving group, and they can develop this. So what it does is, this one now just develop this, and then you can have this one after just an H2O leaving group. Okay. Water just leave it by itself. So this is the main contrast. In the one at the top, you have OH minus is strong nucleophile, so they're going to attack, forcing this one to leave, right? Where here you have a very weak nucleophile, kind of weight, but this one is what is attached to here is they are itching to get rid of this. They are itching to leave here. So why don't I just leave first? And so this is the first unimolecular dissociation that this one happened, and that's a slow step. This is a rate determining step. but that's what happened first. And then now you are going to see this chlorine is going to make a bonding with a carbocation up there, right? And this is actually interesting. That it's a lot more complicated than I thought. Once this ever happened, do you see what I'm getting at? I made this. I just made it up, this problem, and I made you guys give you a headache here. Okay, so this is this is a secondary carbocation, right? But if you look at that, okay, there's a hydrogen. Can I do the hydride shift? Yes, you can. And then what you're going to have is you will develop this carbocation with, I guess, so I'm sorry that this is has only one hydrogen. Okay, so this hydride shift, now you do have two hydrogen. So this is a tertiary carbocation by hydride shift. And then we are going to have this one now connected to this side, and then you will see this attachment. So therefore, you will see this methyl, and then chlorine will be attached to this side. To tell you the truth, actually, this one, the nature of carbocation, which is a planar, this is actually going to be a planar here. So therefore, actually, the methyl is on plane with a ring. So you actually either have chlorine up, and this one is down. And so this is the nature of SN1, which is a unimolecular, because it takes energy. The rate determining step is carbocation formation, and that's the one. And then you'll make this mixtures of these two. Whereas this one, the one SN2, is actually, key one is inversion, right? It's more like a flipping the umbrellas by showing this, and that has been discussed in the Dr. Ma's class. Okay, so the second one is actually, I tried to look for the example of where Dr. Ma's discussed about E2 elimination. This is an E2 elimination. E2 elimination means bimolecular. So now you start to getting a sense that elimination, but elimination means you are talking about base. Okay, so we call the base. And this base is looking for protons. Okay, they are trying to make a bonding with the protons here, and then where do I look for? And this is a bimolecular, means this CH3O minus, which is a methoxide, and lithium is a plus. This is a very strong base. Okay, when you have this strong base, this lone pair electrons over there, they are going to look for some hydrogen. So they're going to hover around, and they're going to look for the hydrogens. So where do they take the hydrogens now? They can take the hydrogens. Let's use a different color, probably to highlight. There's a hydrogen here, right? There's a hydrogen here, and so you are looking for. This is a leaving group, and there's a carbon attached to it, the adjacent. The one that next to the adjacent carbon group contains a hydrogen, and that's the one that this is going to go and then take it out. So in the more drastic sense. So this is one that they are going to go. Okay, I'm looking for hydrogen to take it out, because this is, to me, is a base. Okay, they're looking for the H plus. So by doing so, this bond is going to form the double bond here, and so therefore this carbon here has a 1, 2, 3, and then there is actually extra electron, extra hydrogen here before, but now being forced another bonding, they have no option but to just forcing this chlorine to leave. So it's more like this one is push, and this is being leaving at the same time. So there are two molecules involved with this reaction at the same time. So it says that E2, so I can take the advantage of this wording here and saying that, okay, so then what am I seeing here is, I see this trimethyl, this one coming out, and then this carbon will form the bonding, double bond, and then they will form these structures, and the chlorine is left, and then I think that I guess the hydrogen is still there. So this is a compound that has been made up by this. Okay, so this is when your case of the E2, and E2 means you need a strong base. And here's an example of CHO minus. And strong base and strong nucleophile is going side by side. Another example is hydroxyl group. These are the strong base. They love to take the H plus and then neutralize. They become the zero charges, right? And then what you see here is okay. And then what I have a chlorine minus leaving group, and then you also have your base methoxide becomes an alcohol. And those are the, he said, 3 products, and then I think that's what he mean by that. And then probably lithium chloride is a spectator ion before and after occurring the same way. So I like to give you a contrasting example here. And so let me just draw the same one, but this time I wanted to draw you. So I'm drawing this tertiary methyl, and then this one is chlorine. Chlorine is actually not a bad leaving group. It's not really excellent leaving group, but it's not bad. So I will just keep the same problem as they are. So this is original molecule, but this time, let me just say I have a very weak base. I don't know what's the weak base. Something like, well, let me just say weak base, okay? So the example of weak base is like H2O is probably weak base too, but let me just say it doesn't occur to me right away what's the good example of weak base. So if you have a weak base, and what's going to happen is this is will have a E1, means just in a way self-generated carbocation by having this chlorine as a leaving group. Okay, so what's happened is, okay, so this bond, they will just leave it. This is a weak base. This base is weak, so they are not doing anything, but they just wait. Okay, they just wait, just like an SN1 reaction. They just wait. So then what they're going to happen is they're going to make this the carbocation. Right? And when you see the carbocation, and this is a secondary carbocation, you always ask a question that, can I make it into a third carbocation? Tertiary carbocation. And the answer is yes here. Okay, if you look at here, there is some hydrogen supposed to be there, and this one is all saturated, so there will be a methyl. So this is a case where when this one moves to here, make a bonding, it's an hydride shift. And then what are you going to have? You have a tertiary methyl, something like that, and then this one with this. And then I guess this is just a hydrogen that has moving out, and before you have a hydrogen before, so you have 2 hydrogens there. Okay, so that's the hydride shift as a result of hydride shift. That's the one. And the second option that they can do is a methyl shift. Okay, so what do I mean by that? If you look at that, this methyl also can move around, and to compensate that, by doing so, you are making the positive charges here, and this one has a methyl, and then there will be like this, right? So, okay, so I'll just get rid of the hydrogen just to looking at the differences. Okay, so this is a tertiary carbocation, not a problem. That's also tertiary carbocation from what used to be this. So this is a hydride shift or methyl shift. This is a pretty actually complicated problem. And then what's the nature's choice? They want to move something lighter, right? The hydride shift is their choice, so this will be their choice. Okay, so now because this is a moving on a much heavier element, so this is less favored. So that's my choice for making this. And then what you need to complete this elimination one. So now need to lose H plus. You need to lose an H plus and form because of the base, right? So here, this is the carbon, and that's the carbon. So I'm going to use a hydrogen over there, right? So by doing so, you will see the double bond with this. So what I mean by this in the more clear way, the weak base, although it's a weak, they're going to take it. They're going to take the hydrogen H plus, right? They're going to take the H plus away, and this one will form the double bond, and that's the product that you will see over here, right? So this will be the product for this kind of experiment when you're doing in the, what do you call the E1 reaction. And then, I don't know, you guys can see this, my pointing here, this molecule and this molecule is essentially the same. So whether regardless of which way does it do, I think it happened to be the same product as you can see. Some of you actually pay a close attention to it. They might ask me that, wait a minute, I think that this is a carbon, right? So there must be a hydrogen here. How about this one is taking this is a second option, right? Option that you can consider. And what's going to happen if you do that, if you ever do that, you will end up making tertiary methyl is the same, and here, and then because of that, you will make a double bond here, right? And so then you will make double bond here and this one, right? So I'm talking about this versus this. And which one is going to be favor? This will be a favor. And this is the reason is because of the what is called the GAITSEV rule. Jivestep's rule, and this is the one that most substituted alkane is what the nature prefer. Because you have what you see up there, you only see the double bond has two attachments, right? Here, this double bond has 1, 2, 3 attachments. So this is what they are going to favor for this kind of reactions. Okay, so E2 mechanism, I also were able to kind of find this from the Dr. Ma's slide and exit out. So you take this one, you're losing this, and so you develop this carbocation, and so this is your rate determining step, right? So therefore, your rate here is just, let's say, this compound, if you call this is a alkyl halide, multiplied by alkyl halide. Right? It is not, the rate is K times alkyl halide with and base. Right? And this is for the E2 mechanism because you need both of them actively participate in the reaction, and whereas the E1 mechanism, that's the one only depends on the concentration itself. So this is for E1 mechanism. So by looking at the reaction rate kinetics, you can figure out which one is the mechanism that is important. And this is understand the mechanism is very important. Sometimes you ended up getting racemic mixtures and then not, and that's a thing that we need to consider. Okay, so let me challenge you. Okay, so this is a quiz clinical problem. Is Dr. Ma solve this one with you guys? What is the answer for this one? Dissect rule. Anyone can type the answer? So when you're making this elimination, you're making the double bond, and the more substituted, the better, right? So if this is a more substituted, the better. So most substituted alkene is what the elimination product will prefer. Then try, for example, if one of the answer is this, and this is prefer because that's more substituted, and this is a example of the slide that I find it, and this is a favorite product because double bond has more attachment to do that. This is also the slide that I like to recap, and SN2 is essentially you have a carbon with this is a tetrahedral, and let's say this is a bromine, this is a hydrogen, I don't know, this is a methyl, and this is a methyl. And what's going to happen is your nucleophile attack from the back to have essentially carbon with the nucleophile form the bonding, and hydrogen, I guess, still being there. And then you are losing the bromine minus, for example, here. If I say the minus, I'll be happy. It will be okay. So what that means is a backside is the what they're going to form the reaction. Okay. If you look at this, the one that many textbooks are using this analogy is this used to be the bromine on this side and the nucleophile, trying to make a bonding, and essentially you flip it, the geometries, because after bromine is leaving it, it's an inverted structure. Okay, so the tetrahedral has an inverted, and you see the inverted is, you can see it over there. So make sure that you guys can study this. So I like to draw this one to drawing some my favorite table. This is my first time to draw this table, and I want to show this table to you, and then that will be the end of it for today's recap. So we talked about SN1 and SN2, which is the unimolar versus the bimolecule, and the whole idea is when you have this one is going to be a unimolecule, the rate determining step, this one has to be a good leaving group, right? And so they can just make this activated species, and because of nuclear substitution, the nucleophile is going to react with a carbocation center over there. So does here too. E1, the leaving group is a good leaving group. They make the carbocation, and then the base is going to look for something that the carbocation's neighboring carbon's hydrogen, they're going to take this H plus away, and therefore this one will form the double bonds here, which is shown in this step. Okay? So that the unimolecular has something to do with this nature. So the leaving group is more important onto this. But now let me do the different coloring about the binary molecule, and which is now binary molecule, SN2 and E2. This is actually emphasis a lot more here. The nuclear, if your nucleophile is very strong, they're going to push and they're forced to leave. Right? So this one is forced to leave. So there are two. So this one means that you are talking about strong nucleophile. Okay? So that's here too. This one, they are strong base looking for hydrogen. Right? This is a hydrogen. These electrons are being stripped away. So this is hydrogen. They're going to form the bonding and then forcing this one to force to leave. So I'm going to make just give me one more minutes, and then I think the 2 minutes, and you'll be happy to see these tables that I think I'm showing up here. Okay. So what I'm drawing here is I'm going to make a table. And this table, what I'm drawing here is if you're talking about nucleophile reaction, if you're talking about base reaction, and if this is a strong nucleophile, and we are talking about SN2 reaction, and that should make sense to you. Okay, when you say nucleophile means already you're talking about nucleophilic substitution reaction, because nucleophile it can push because it's strong, so bimolecular reaction can happen. And when you talk about the base, and base is strong, they can eliminate the proton to create the double bond, but you are forcing it, so it is a bimolecular reaction. Okay, so in other way, when your nucleophile is weak, they are not doing anything. They're gonna just wait, right? In a way, they're going to just wait. So therefore, until the things are leaving group is leaving as it is, so in a way, in a very simple sense, that's what's going to happen. So that's here too. They're just going to wait until they develop carbocation, right? The leaving group leaves, and they develop the carbocations, and then if needed, they can do the carbocation rearrangement. But the thing is always a unimolecular. So by looking at this table, you can develop this concept. This is very simplified table, but it will be a useful guideline for you to. Thank you very much. I think you stay with me, and I think we have more people join in, and then that's great to see you. And I just I finished recording this, so I